Today, we will be dealing with the famous Gaussian integral, where we have to find the exact value of the integral of e raised to minus x squared from minus infinity to plus infinity. This integral is one of the most important integrals in all of mathematics. It appears in probability, statistics, physics, engineering, and many other fields. The surprising thing is that nobody has found an elementary integral formula for e raised to minus x squared. So the usual integration techniques, such as substitution, integration by parts, and partial fractions, do not work here. Most textbooks solve this problem using polar coordinates. However, long before that method became popular, Pierre-Simon Laplace discovered a beautiful solution that avoids polar coordinates completely. Let us see how he solved it. For that, we let the value of the Gaussian integral be called I. Now, since this is an even function, minus infinity to plus infinity becomes 2 times integral 0 to plus infinity of e raised to minus x squared dx. Great! Now, since we do not know how to evaluate this integral I directly, Laplace decided to look at I squared instead. When we square I, we are multiplying the integral by an identical copy of itself. But we will make one small change. For the second copy, we simply replace the variable x by another variable called y. Since variables inside an integral are only placeholders, changing the letter does not change the value. Multiplying these two integrals together, we get 4 times double integral from 0 to plus infinity of e raised to minus x squared minus y squared times dy times dx. Noise. At this stage, using the traditional approach, we would have switched to polar coordinates. But Laplace chose a completely different path. He introduced a new variable by writing y as t multiplied by x. Next, we differentiate both sides with respect to t. At this stage, x is treated as a constant because we are allowing only t to vary while keeping x fixed. Therefore, differentiating gives dy equals x multiplied by dt. Also, when y equals 0, we get t equals 0. Similarly, when y approaches infinity, t also approaches infinity, assuming x is a fixed positive value. Substituting y equals tx into the exponent gives e raised to minus x squared minus t squared multiplied by x squared. Both terms contain x squared, so we can factor it out. This gives minus x squared multiplied by 1 plus t squared. After replacing dy with x multiplied by dt, an x